Now, I do want to talk about the two types of mechanical waves that we have. We're going to have either transverse waves or longitudinal waves, and really the only thing that differentiates these is whether the particles are moving in the same direction as the wave or whether they're moving perpendicular. So if you were to think about a slinky and take the slinky and wiggle it back and forth just like this, then you're definitely sending pulses down it. And you could kind of say that the pulses would go from your hand probably down to the wall. And in this case, the particles are moving side to side, and the wave is also moving side to side. So this one is actually going to be a longitudinal wave. You could also take the slinky and shake it up and down, kind of like this. In this case, you would actually visibly see the slinky. The particles would be going up and down, but the wave would actually be traveling in this direction right here. So we're actually going to go ahead and we're going to call this guy a transverse wave. Now, we can still talk about things like the wavelength, the speed, and all this stuff. It's going to apply to both. In this case right here, we'd say, well, the wavelength is going to be, one full trough-to-trough distance for the transverse wave, but you could also say that the same thing is going to apply to the longitudinal wave. So where is it all bunched up? And these two guys actually have the same wavelength. Now, this just kind of says everything that I already said in the last one, just with some text associated with it. Transverse waves, the medium is going to move in a perpendicular direction to that of the energy transfer. So the wave, the particles will be wiggling up and down. The wave is going to be traveling, say, side to side. Examples of this would be, if you pluck a guitar, the guitar string is going up and down, but the wave is kind of going side to side. Things like radio waves and light waves are also going to be transverse waves, where the medium is moving up and down, and the wave is moving side to side. You could always think about this as whenever you go to a football game, and then you have the mascot, and the mascot runs down the field, and first this person's going to stand up, and then this one will, and this one will, and then this one will, and then this person's going to sit down. So you can think of the people as the particles, and you can think of the wave as going in this direction right there, so that would be the direction of the wave, but the pulses would be going up and down. So two adjacent peaks, the distance between them is going to be the wavelength, and that's going to apply to both transverse wave and longitudinal waves. So the vibrations of a transverse wave are going to move in a direction that is perpendicular to the wave propagation. Now I want to talk about longitudinal waves. That was when you were taking the slinky and shaking it back and forth towards the wall. I always like to think of a nice line of people, and at the back of the line of people it seems like you always had the bully. And that bully is going to be mean, so he's going to shove the person in front of them, who's going to shove the person in front of him, shove the person in front of him, shove the person in front of him, and so on and so forth. In this case, the particles, they're moving in the side-to-side direction, and the wave is moving in the same direction. So this is going to be a longitudinal waves. Again, both of these types of waves are going to transmit energy. The person at this end of it is going to get that energy. And again, the medium is just going to go parallel or in the same direction as the energy propagation. Examples of this would actually be a sound wave. Sound wave is always going to be a longitudinal wave where the particles are moving back and forth. So you could think of having a speaker, and this speaker is just a membrane, and that membrane is going back and forth. It's causing all the air that's inside of the room to bounce back and forth, so the particles are kind of going back and forth. And then we're going to have your ear right over here, and that ear is going to be able to hear the sound, and so it's going to be a longitudinal waves. The waves are propagating in that direction, and the particles are also kind of moving back and forth. Bear in mind, the particles themselves don't have to make the full path. So picture just for a second, we had a tuning fork, and what we're going to have is we're going to have it vibrating, and it's going to compress the air in certain regions. We actually have a special name for these. We call these guys compressions, where the air has been compressed together, and it looks like it's been compressed. And we also are going to have what we're called rarefications, where there's not a lot of air. All the air is kind of tied up right in here. Now, we can also talk about things like the wavelength. The wavelength is going to be a peak-to-peak distance, and it's a little bit harder to visualize, but you can kind of see this right here would be one full wavelength, one full peak-to-peak distance. So again, for longitudinal waves, it's going to be the distance between compressions, or it could be rarefication. So it could actually be both of these. Remember I said it could be crests or it could be troughs. So let's go ahead and talk a little bit about wave interference. We can have two waves living at the same place and the same exact time, and we have a special name for that. We're just going to say that these waves are going to superimpose, and they can interfere with one another. They can add together, or they can subtract themselves out. we kind of have a special name for this. We're going to say, suppose I have a location, and I have two waves, and one wave is going to look like this, one wave is going to look like this, and you could even think of these as being waves on a rope. And if this piece right here is pulling up, and this piece is pulling up, then they're both going to pull up, and at the end of the day, the rope is going to be pulled up by about twice as far. So these guys are going to reinforce, and they're going to do what we call constructive interference. Now, picture for a second I had a rope, and here it's pulling up, and right here it's pulling down, and these two guys are actually going to cancel each other out. So, cancellation. We have a special name for this. We just call this destructive interference. Now, suppose I had some water, and I went ahead and I took, a dabber right here, or a dabber right here, and a dabber right here, and I plucked them up and down pretty much at the same phase. Then what's going to happen is these water waves are going to sometimes add together. They're going to have constructive interference, and sometimes they're going to cancel out. They're going to have destructive interference. When they arrive at the same place at the same time, and they're both, kind of pulling up like this, then we would say they are in step or in phase with one another. But if they arrived totally out of phase, then I would say they're out of step or out of phase, and then they're going to cancel each other out. You can kind of see that, there's regions along here where sometimes they add together. I'm going to try to highlight it right here. There's regions where they sometimes cancel each other out. So we're going to have regions of constructive interference and regions of destructive interference. Now, I do want to talk about one special case of interference. I want to talk about something called standing waves. If we were to take a rope and tie it to the wall right over there, and we were to send a wave down it, so picture an incident wave kind of going like this, then what's going to happen is if it's shaken at just the right speed, then the incident wave and the reflected wave are actually going to have a special case of constructive interference. And they're always going to add together in certain places, and they're always going to cancel each other out in certain places. So we're actually going to have what's called a standing wave, a wave that looks like it's just kind of standing there. Now we're going to have regions where there's no movement whatsoever. We have a special name for those. We're actually going to call these guys nodes. And we're actually going to have regions of maximum displacement. We're actually going to go ahead and we're going to call those guys antinodes. So again, nodes are going to be very little or minimal displacement. Antinodes are going to be maximum displacement. And we can get a standing wave that kind of looks like this. And so here we would have an antinode, we would have a node, we would have an antinode, and actually we would have a node here as well as a node right there. These guys are pretty much always equally spaced from each other. But there's more than one way I could set up a standing wave. If I were to shake it, to shake a slinky or something fairly slowly, then I could have a case where it would always go up, and it would always kind of come back here just like this. Or I could shake it a lot faster. And you could picture me, taking a slinky and shaking it a whole lot faster. I could also set up a standing wave that would look like this. And I could also shake it even faster still, and I could set up a standing wave that would look like this. Now, keep in mind that one full wavelength is going to be one full up or one full down. So in this case right there, one full wavelength would actually be equal to 2 times the length of my slinky right here. This guy right here, well, one full wavelength would be equal to the length of my slinky. And here, actually, there's one full wavelength and there's a half a wavelength. So now I actually have 3/2 of a wavelength being equal to the length of my cavity. Now, incidentally, the wave speed is going to be the same for all these because the tension is always going to be the same and the mass is always going to be the same. So what's happening is we're shaking it faster and the wavelength correspondingly has to change. Now, we are also able to set up standing waves not using a slinky, but inside of containers, and we'll talk about this a lot more in the next chapter. We could talk about waves on a guitar string. Those guys tend to be standing waves, and we can also talk about waves in open pipes or closed pipes inside of a trumpet. And what we kind of do is we kind of mess around with how long it is, and that's going to change the sound. One thing to bear in mind that if we were to have a guitar wire, and we were to go ahead and we were to pluck this thing, usually what sets up is going to be what we would call the fundamental frequency, the easiest one to set up, the one that kind of looks just like that. Now lastly, I want to change gears a little bit and talk about something called the Doppler Effect, which is going to answer the question, what happens if the source is moving, or what happens if the listener is moving? So picture for a second that you're walking down with a boombox and it's putting off some sound. And if you're not moving, then what you're putting off is you're putting off sound waves that are going to kind of be equally spaced just like this. But once, let's just say the source starts to move, then what happens is the source tends to start to walk into its own waves. So here I put the source moving like this, and you can kind of see right here the wavelength is going to actually go down, and the waves tend to close in upon themselves. Now, the speed of sound is going to be what the speed of sound is, and so actually the frequency is going to correspondingly change, and right over here you're going to hear something that is high-pitched. Now, behind it, you're walking away from those guys, and so the peaks or the crests are going to be further apart, and so the wavelength is going to be smaller, kind of behind the source. Now, it does also apply to light as well. And what would happen is if the source is approaching you, then it's going to increase the frequency, and it's going to decrease when the light source moves away from you. And you can actually see this with spinning stars. We would actually talk about stars that are blue shifted or stars that are red shifted. The blue shift, the star is moving towards you, so it's going to increase the frequency. Red shift, the star is moving away from you, so it's going to decrease the frequency. And this actually even tells us something about how fast the star is moving. Now, a Doppler effect is going to occur for both sound and for light. Now, you may ask yourself, what happens if a source moves at just the right speed, so all of the crests in front of it tend to pile up in front of it? So here we have a bug, and what if that bug is swimming as fast as the wave that it makes? Well, here all the crests are going to pile up, and we're actually going to have what we would call a bow wave. Now, here we have a bug, and the bug is moving at some speed at less than that of the water, and here we're going to have a bug with its speed equaling the wave speed. Now, what happens if the bug goes faster than its wave? Well, what we're going to do is we're going to get this bow wave that kind of bends out just like this, and actually the steepness of its angle is going to be related to how much faster it's moving than the wave speed. This is actually just like the waves that you see behind a boat, the waves that are really fun when you're like on jet skis and stuff like that. Now, when an aircraft does it, suppose an aircraft flies faster than the speed of sound, then we're actually going to say it's supersonic. We could even talk about Mach 1, Mach 2, or Mach 3, and that's just, is it 1 times the speed of sound, 2 times the speed of sound, or 3 times the speed of sound? Now, what's kind of happening with the wave here is we're actually going to have a shock wave. So you can kind of see that all the air molecules are packing up right there, and all the air molecules are packing up right there. That's when this aircraft starts moving at a speed that's faster than the speed of sound. And pretty much every surface is going to have this. So picture an aircraft moving at 1 times the speed of sound. We're going to have really high pressure right there where all the air molecules are being jammed together. And then right back here, then the air molecules are actually being pulled apart. So we're actually going to have low pressure right there. And when we talk about a shock wave, we're going to have a high pressure wave and a low pressure wave. It doesn't mean that this aircraft has to be noisy. All it means is the aircraft is packing all the air up together in the same place at the same time. Now, what's going to happen when we have an aircraft that's moving faster than the speed of sound? Well, we're actually going to hear a sonic boom, and bear in mind that the sonic boom is not going to be directly below the aircraft. It's going to be slightly behind the aircraft because it has this little V pattern that fans out faster, or fans out behind it. All it's really saying is this aircraft broke the sound barrier and it piled all the air molecules together. We could also have other examples. We could have a bullet that's going really fast, or even the crack of a circus whip. The crack of a circus whip, the tip is actually going faster than the speed of sound, and so you're going to hear a shock wave.